Hi, everyone, and welcome to our lecture video combining units 5.4, 5.7, and 5.8, talking about elementary reactions, reaction mechanisms, and their rate laws. By the end of this lecture video, you will be able to identify the overall reaction from a series of elementary steps and articulate the intermediate and catalysts for different reaction mechanisms. So far in our chemistry journey, we have been given chemical reactions, just as one chemical reaction. However, very few reactions actually occur as they are written. So for this reaction here, it seems like we have two nitrogen monoxides and it reacts with oxygen gas to produce two nitrogen dioxides. However, if we actually did this reaction, N2O2 is detected during the reaction. But what I notice is N2O2 isn't a product here. Yet I'm detecting it if I were to actually do this reaction in the lab. The reason this is because this reaction doesn't just happen in one step. It actually happens in multiple steps. And those multiple steps are called elementary steps. And when I have a sequence of elementary steps by which a chemical reaction occurs, we call that a reaction mechanism. So a reaction mechanism are both of these elementary steps here. The mechanism itself tells us that for this reaction to occur, elementary step number 1 occurs, and then elementary step number 2 occurs. Elementary step number 2 cannot occur if this first step does not happen. And then from our reaction mechanism here, which is showing our two different elementary steps, the sum of these steps of our reaction mechanism actually give us our overall reaction. So let's talk about how I go from my elementary steps in my reaction mechanism to my overall reaction. For me to figure that out, all we have to do is add these two reactions together. So let's think back to when we were balancing redox reactions and I added up my two different half reactions. One of the first things I made sure to help you articulate is, are there species that are on both the product and the reactant side? And we look at our reaction right here, and I notice N2O2 is on the product side here in elementary step number 1, but then it's also on the reactant side here in elementary step number 2. And because it's both on the product and the reactant side, in our reaction mechanism, they will cancel out, meaning this specific species, N2O2, is not going to be in our overall reaction. If I notice now, NO and NO here is not, they're only reactants, they're not products. Oxygen gas is only a reactant, it is not a product. And NO2 is only a product, it is not a reactant. So I've canceled everything that's on both sides of our equation. And now when I go to add these up, I can get my overall reaction, which is NO gas plus NO gas, which is another fancy way of just saying two NO gases react with oxygen gas to produce 2NO2 gas. So when we have an overall reaction of 2NO reacting with O2 to produce 2NO2, just like how I talked about on the previous slide, this overall reaction doesn't just happen as written. It actually happens in a series of 2 steps. Those 2 steps, when combined together, form our overall reaction. Our 2 elementary steps, part of our reaction mechanism, can be added together to find our overall. Something that you might have noticed that I haven't addressed quite yet is that here on the right side, we notice the relative speeds of each of our steps. Our different steps generally do not happen at the same rate. That means one is going to be slower than the other. We note the slowest step by just putting in parentheses slow, and we put faster steps in parentheses just as fast. What we do is we're able to say that our slowest step, so here, elementary step number 1 is noted as slow. The slowest step is called our rate determining step. And this is because the rate of the reaction is only dependent on this specific elementary step. So when you are asked and you're given a reaction mechanism and you're asked to write the rate law for this reaction mechanism, the rate law is derived from the slowest step. So let's take a peek here before I give a really big disclaimer. If you are asked, you're given a reaction mechanism like this, and you are asked to write the rate law, our skeleton structure still applies, right? We have our rate, as always. The skeleton structure, what I mean by that is rate is equal to our rate constant K times our reactance. We'll call it generally A for now, to some sort of power X, right? So far, that's our skeleton structure that we've talked about. For a reaction mechanism, we look at the slowest step because it's the rate determining step. So I'm only looking at this reaction for my actual rate law. So when you're asked to derive the rate law for this reaction, we look at the slowest step, and I'm able to say that the rate here is equal to our rate constant K times our reactance here. My only reactant is NO. And when you're given an elementary step as part of a reaction mechanism and you're told it's the slowest, now you can use your coefficients as your order. So I notice there's one NO2, there's two NO2s. So my rate law for this reaction is K times the concentration of NO squared. Notice, this might have sent off a little bit of red flags because early on in this unit, I said you cannot use your coefficient to figure out the order. When you are given your reaction mechanism and you're identified and told what the slowest step is, now is the only situation that you can use your coefficients. And this is going to be connected to our idea of collision theory, which we're going to talk about in the future class. So just to reiterate the big disclaimer that I said, the coefficients of your reactant species will be the order of the reactant in the rate law only for elementary steps. And again, you will be shown explicitly your reaction mechanism. You will never be asked to predict your reaction mechanism. It is something that you will always be given. This is a big contradiction to what I said earlier on. The reason I said that big disclaimer early on is because I only gave you overall reactions. So if I'm given an overall reaction, we cannot use coefficients as our order. However, if I am given a reaction mechanism with the slowest step, then the rate law order of reactants are the coefficients. So hopefully this distinction is clear. You will only use the coefficients for the slowest step in your reaction mechanism. But if I'm given one chemical reaction, we assume it's an overall reaction, and you cannot use coefficients to identify the order of your reaction. So last conceptual piece of information. Here we have a new reaction mechanism showing that nitric oxide decomposes ozone in the upper atmosphere. We have two elementary steps here. We're told specifically that in elementary step number 1, we have NO and O3, and it reacts to form NO2 and O2. Then NO2 here goes on into elementary step number 2 and reacts with O to produce NO and O2. So if you were asked to find the overall reaction, as always, we're going to go ahead and add these two guys up. But along the way, we notice I have to cancel out what appears on both sides. The first thing I notice is that NO is produced, and then it's a product at first, and then it's a reactant later on. The species This species in particular is called an intermediate. So NO2 in this reaction is an intermediate because it's a chemical species that is produced in an early step. It's a product early on, and then it's consumed in a later step. We notice product earlier, reactant later. So we would say that NO2 here is our intermediate in this reaction. Because it's both a product and a reactant, ultimately, all intermediates will be canceled in our overall reaction. However, it's not the only species that's noted here that will also cancel out. If I take a peek, nitrogen monoxide is a reactant early on, but then I notice it's also a product later on. This species will cancel in our overall reaction, but it's not an intermediate. We call this species a catalyst. A catalyst is a chemical species that is consumed in an earlier step, meaning it's a reactant earlier, and then it's produced in a later step, meaning it's a product in a later step. A catalyst, and we're going to explore catalysis and catalysts in our last unit of our last section of Unit 5. Catalysts also speed up the rate of our chemical reaction. Our catalyst in this actual reaction here is NO. So both NO and NO2 will not appear in our overall reaction, but those actual species are different from each other. NO is our catalyst and NO2 is our intermediate. But again, both of these cancel. NO is a product, but it's also a reactant. So when I add them up, they cancel out. And then NO2 is a product, but it's also a reactant, so those cancel out as well. So my overall reaction is going to be ozone, O3 gas, plus singlet oxygen, oxygen gas, or excuse me, singlet oxygen, reacts to form 2 O2 gases. And that's my overall reaction. Now, we're not shown here, but let's say I told you that our slowest step is first, and then we have a faster step later on. If you were asked to write the rate law for this reaction, we're able to say that our rate is equal to our rate constant K times our concentration of NO times our concentration of O3. Still both of my reactants, specifically of my slowest step. Notice I do not put the reactants of my fast step because my rate law is only dependent on the slowest step. So I have my reactants here, and to find their orders, I use their coefficients. Here I have 1 NO, so my coefficient of NO is 1. And I have 1 O3, so my order of O3 is 1. So this would be my rate law for this reaction, and I can only use the coefficients again because it is specifically of the slowest step of a reaction mechanism. You're going to have a practice problem pop up on your screen in just a moment, but that is the end of today's lecture video, and I will see you in next class. Bye, everyone.